just like the spokes of a wheel. These are electric field lines. Okay, now, is this something we can actually see? No, the idea of electric field lines is really just a construct. It's really to help us visualize the forces that are generated around the charge. Is there really such thing as any field line? Is there any kind of line coming out of the charge? No, there's not. No. It's only if you will, a mathematical construct, but it's very, very, very useful, and it's been around for over 200 years, and therefore we're going to stick with it. And there are other uses of the field. The idea of electric field is a very, very, very useful concept, and we will describe that more as we get into it. Okay. But the way it works is this. If I have, suppose this is a really, really big charge, and I put a small charge, a very small charge, a very small plus charge right here. And this is small little, what I'm going to call a test charge. Okay? This test charge, this positive charge, this is always defined with a positive charge as what I call the test charge. What kind of force? There's going to be a force experienced on here, right here. Okay, and what is the size of that force? The size of that force that this little charge is going to feel is going to be K times big Q times little q divided by r squared. R squared is this distance from here to here. Okay, now the electric field, remember that's a vector. It's a vector pointing to the right. The electric field is defined to be, remember it's purely a definition, is defined to be the electric force, the electrostatic force divided by the test charge Q itself. So what that means is we will get K, Q, little q, divided by R squared, divided by Q. Well, the Q's cancel out, and what we're left with is that the electric field is simply K times Q over R squared. Okay, so notice that the electric field here is only related to the size of this charge and the distance away. The electric field, the only purpose of this little test charge is really only what we say is placed there. It's a very, very small little charge placed there for testing purposes to test the direction of the force. Okay, so but it divides out when you calculate the electric field. That little plus charge, that's just an imaginary little plus charge, divides out. So the size of the electric field is not even related to it at all. It's only there just for convention. So the electric field, basically, we can think of it this way. At this point here, the electric field is simply KQ divided by R squared. Now this is only true, this formula that's in this book, this formula for electric field that I've given you right here, is actually only valid for a isolated charge with no other charges in the middle. And we'll talk about this more in a bit. But this is the concept of the electric field. The further out I go, suppose I put a test charge way out here, plus Q, and I want to calculate the size of, the electric field, but way out here. Well, it will be simply K times Q over R squared. Again, the little q cancels out, and this R is much larger, so R squared is much larger, so the size of the electric field gets smaller. The further out I go, this, because this is by R squared, goes by R squared in the denominator, the size of the field gets smaller and smaller and smaller. And then when I finally get all the way out to infinity, the size of the electric field goes to 0. Okay. Well, so suppose I now had a negative charge That's for a positive charge. If I had a negative charge, say this was a negative Q, the electric field lines come into a negative charge, so it would be the exact same thing. It would look just the same, except the direction of the electric field lines are coming in and not out. The electric field is exactly the same. Notice if I put a plus charge here, there's a force what way? This way, into it. And the electric field, again, will also be, it's oriented into the charge, will be K times big Q times R squared. Okay? Again, the electric field, if the force is oriented one direction, the electric field is oriented in the same direction. The force and the electric field always are collinear. In fact, the electric field tells you what direction the force is, and vice versa. Okay. Now, what happens if you look on the next page, page 441, and the next couple of pages, they start drawing some diagrams here about how multiple charges interact with regards to electric fields. Look at page 441 and page 442. And there's 3 rules. If I have this, minus charge and a plus charge, this would be over on page 442. There's 3 general rules, and those 3 rules of how to draw electric field lines are stated on page 440. You have to know this. This will be on the homework, and it will also be on the test. In fact, the test will ask you to draw certain electric field lines in different configurations. So you will have to know how to do this. The rules, there's 3 rules. The rules are at the bottom of page 440, and they are, number 1, the relative number of electric field lines drawn is proportional to the charge of the particle creating the field. We'll talk about that in a bit. Number 2, the arrows that form the electric field point out of an electric charge and point into a negative charge. Number 3, electric field lines can never cross. Sounds easy, but it's just the way it is. So sometimes it's a little bit hard to see how you draw these. But basically, here's how we start. If we have this configuration, a plus charge and a negative charge, how do we draw the electric field lines? Say they're +1 and -1 coulombs. So the exact same charge. There's going to be, if I draw 6 field lines coming out, I have to draw 6 field lines going in. So if they're equal charges, there have to be the same number of field lines coming in and out. The number is purely arbitrary. I just have to make sure they match. So I'm going to draw 6 field lines. Here's one. Remember, out of the plus into the negative. That's 3 lines. I'm going to draw 3 more, and I'm going to separate them like here. Okay. This one comes around like this. This one comes around like this. And this one, actually, in general, you could even do this. It goes out to infinity this way, and it comes in from infinity the other way. So these 2 infinities meet. Try to explain that to your parents. See if they believe you. But it's true. That in general, in theory, mathematically, this field line goes to infinity the other way, to the left, and the field line all the way from the right comes in. Do these 2 infinities meet? Well, they're connected, believe it or not. They are connected. So this would be an example of how you would draw the electric field lines in one particular case. Now, the other thing I'd do, if I didn't want to do this, I could just leave it like that. There I have 5 field lines, and that would, see, 1, 2, 3, 4, 5, 1, 2, 4, 5. I have 5 lines coming out of the plus, 5 lines going into the negative. Okay, that would be how you draw it. Suppose the configuration is +1 and +1. So +1 Coulomb, +1 Coulomb. That would be like on page 441. Okay. the charge, a charge, I'm gonna draw 6. I'm gonna draw them 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, the lines cannot cross. They come out of this charge, but they also come out of this one. But notice, do any of the lines from here go into here? No, they cannot. So what's going to happen is they're going to go like this. Lines from here are going to go out, just kind of like the radial or the radial case. And what's going to happen here is they're going to start to bend. That's maybe a bad drawing, but what happens is that these field lines, they cannot cross each other, but one, because they're both plus charges, they don't go from here to here. They have to diverge. So there's an area right in the middle here. If you look as symmetrical, this is not a very symmetrical drawing, but the field lines diverge away from each other. So there's a point right in the middle, right here, mathematically right in the middle, where there's actually zero, where the electric field here is actually 0. And what does that mean? That means that the force is 0. Now, why would that be? Well, think about it. If you're right in the middle, the exact middle of two plus charges, remember these are repelling each other. Suppose you're a little plus charge. They are repelling. The forces are, the charges are repelling each other. If you're a little test charge right in the middle, you feel equal force one way versus the other way. They're repelling both ways, so the forces exactly cancel out to have 0 force, and where there's 0 force, the electric field is exactly 0. So there would be a mathematical point right in the middle where there would be 0 force. Okay, now suppose you had the situation like page 442, for instance, where this is plus, I'm going to just make up one. This is plus 2, but this is negative 1. Okay, remember this has twice the charge as this one. So so if there's, let's say 6, well, let's make a number. Let's make, if there's 5 lines coming out of here, then there have to be 10 lines coming out of here. Okay, since this is double the charge, it has to be much more, twice the number of charges coming out. Okay, so I'm just going to, so let's see if I can do this. How would it look? Remember, the lines come out of here, so here's 1. Okay. Here's 2. Here's 3. Here's 4. Here's 5. Okay. So all these 5 from here go into here, but they have to have 5 more. These 5 more have to diverge out this way. 2, 3, 4, 5. So these 5 lines can't come around to here. So it would look something like this, where half of the lines from 2 go into 1, but the other half have to go out somewhere else, out to the left. So it would look something like that. Okay, now how do we practically use the electric field concept? And that's what we're going to just look at briefly now. Okay, and we're going to use the example on page 444. At first, the concept of the electric field seems a little bit mystifying, but once you get used to it, it's a very useful concept to use. Okay, this is example example 13.4 on page 444. We have two charges. What do we have? We have a plus 0.6 millicoulomb charge here. Then we have a minus 0.3 milli. You know what? I think they have a typo here. They have milli, but I think they're both just 0.3 and 0.6 coulombs. They say milli, but I don't, in their equations, they use it just as there's no milli in here, it's just 0.3 and 0.6. I think they have a typo here. So that's such, and what we have here is right in the middle, from here to here, we want the electric field right in the middle. What is the electric field right in the middle? And this is 0.8 meters, and this is 0.8 meters. Okay, we want to get the electric field right in the middle. Okay, so okay, what is the magnitude of the electric field right here? Okay, well, what I want to do is I'm actually going to well, we're going to solve this. We could solve this problem two ways. We're just going to do it one. What we're first going to do, we're going to, there is an electric field. Remember, electric field's a vector quantity, and the total field will be E1. This is E1 plus E2. It's the sum of the two fields. Okay, so the field, first we have the field. Imagine putting a plus charge, imagine wherever you want the field, wherever you want to test the field at, put a little plus charge here. Okay, and then we have the field generated from number 1. Then we have the field generated from number 2, and we simply add those together. Okay, so it sounds complicated, but really it's quite easy. The electric field generated from number 1 at here would be simply K, and this is, we're going to call this Q1, and Q2 is simply K Q1 divided by R1 squared. Okay, this is R1, this is R2. Okay, so that would be 9 times 10 to the 9th. Q1 is 0.6 C divided by 0.8 meters. We have to square that. So the size of the electric field right here from Q1 is 9 times 10 to the 9th times 0.6 divided by 0.8 squared, and we get 8.4 times 10 to the 9th, and it's newtons per Coulomb. Newtons per Coulomb. Notice, how do we get that? Remember, the electric field is the force divided by Q, so that's in newtons divided by a Coulomb in units. Okay, so that's the force of E1. The electric field E2 is the electric field right here, but from charge number 2. Remember, these are vector quantities. Would be K Q2 divided by R2 squared, which would be 9 times 10 to the 9th times negative 0.3 coulombs divided by 0.8 meters squared, we get 9 e to the 9th times 0.3 divided by 0.8 squared, and we get 4.2 times 10 to the 9th newtons per coulomb. Okay, now let's look at the direction. The direction here is plus direction. Remember, if this is a plus charge, this is a plus charge. This force, this plus little chest charge wants to be pushed this way. So E1, the force 1 and E1 are both to the right. So E1 is to the right. Okay. Here, this is when we regards the Q2, the plus charge is a plus, this is a minus, there is an attractive force, so here E2 is also to the right. Okay, so actually when we look at the directions of the forces and the direction of the fields, remember the force, the electric force and the electric field go in both the same direction. Again, E1 is going to be a force oriented to the right. E2, and so E2, well, the E1 goes to the right. E2 also goes to the right. And so actually, these two are going to add up. They're both going in the same direction. We simply add them up. E1 plus E2, they're both going to the right. So the sum of them is simply, well, here, we'll simply add them here. It would be 6.12 times 10 to the 9th newtons per coulomb. That would be E total, which is the same thing as 1.26 times 10 to the 10 newtons per coulomb. Okay, so that would be the size of the electric field right here, and we add the two components, add E1 and E2 together. Okay, now suppose, the next part of the question is, suppose right in here we dropped a negative, we put a charge in, right at this point we put a charge, but the charge was a negative 0.0006 coulombs. And it was a negative, and it was a millicoulomb. Here, they do use millicoulombs. Okay, so we drop a negative charge in here. And the question is, what is the force on that little charge? So we drop a little charge. I'm just going to write it again. This little negative, it's a little negative charge, 0.006 millicoulombs, which is the same thing as 6 times 10 to the minus 6 coulombs. If you work out the units of that, that would be the little charge. Well, now remember that the electric field, the total electric field is this. So, well, we come back here to our equation. Remember, electric field is equal to the force divided by the little test charge. Well, we can flip that around and say that the electric field times the charge is equal to the force. Okay? So all we do, now we know what the electric field is. That's our net electric field. We multiply it by the charge, and we'll figure out what the force is on a charge that's placed right here. So we simply take 1.26 times 10 to the 10th Newton per Coulomb. We multiply that by the charge, negative 6 times 10 to the minus 6 coulombs. We simply multiply those together, and we get 1.26 e to the 10th times 6 e to the minus 6. We get 7.56 times 10 to the 4th newtons. Okay. So now, what is the sign? Well, we got a sign here, but let's see if we can figure this out. The electric field is going, at this point, the electric field is going to the right. Okay, say right here. I'll put it up here. The electric field at this point is going to the right. If we put a plus charge here, the force on that would send the force. The force on that charge would go to the right. You remember the force goes according to the electric charge when we have a plus charge. But now we have a minus charge, so the force is going to be directed to the left. Okay? Does that make sense? I hope so. That the electric force is always in the direction that a plus charge, the electric force, if the electric force is to the right and we drop in a plus charge, the force is also going to be to the right. The electric force, will always go in the direction of the electric field for a plus charge. But if we have a negative charge, if the electric field is to the right with a negative charge, the force is to the left. Okay, so this actually is the force that's oriented back to the left, not to the right. Okay, so all right. So I hope that problem makes sense, and it takes a little bit of time getting used to working with electric fields. And there's only one more concept we need to go over. And that's very briefly on page 446 and 447. And that real quickly, or I'm not going to spend a lot of time on this, but it's applying Coulomb's law to the Bohr model of the atom. Now, in the lab, this chapter, we have two labs. The first lab is where we're going to have a Van de Graaff generator. But in the second lab, we have a purely numerical lab where the whole point of the second lab is to go over exactly this issue, is to go over, we're going to explore more the in-depth behind the Bohr model. But just briefly, the idea of the simplistic view of the atom is we have a plus, a neutron, and protons, just like we drew before, and we have an electron that's flying around here. Okay, let's take the hydrogen atom first of all, where we just have one proton and one electron. This will be the hydrogen atom. Okay. Okay, in this case, if you think about it, isn't there a Coulomb force between the proton and electron? Absolutely there is. Okay, and the electron, the Bohr, B-O-H, the Bohr model of the atom is that the electron is simply spinning around, flying around in orbit, just orbiting around the proton right here. So we have a certain radius here, and if the electron is moving around the nucleus, then there must be, it's moving in a circular motion, so we know there must be a centripetal force holding the electron in orbit. And we think back to chapter 7, where in 6, I think 7, where we talked about centripetal force. Basically, the Coulomb force is what supplies the force to keep, is basically the Coulomb force supplies the centripetal force necessary to keep the electron moving in orbit. Now again, this is the Bohr model of the atom. So what does this look like? It would look like if this is plus Q, and we'll call this minus Q, okay, which is little q, that we'll call the nucleus plus capital Q and the electron small q, then it would be K Q times little q divided by r squared is equal to the mass mv squared over r. Okay. Where this, what is this a mass of? This is a mass of the electron. This is the electron mass. We're talking about the electron spinning around. So the mass we're talking about here is the electron mass. Okay. So we can take this equation, and can we actually solve this equation? Well, yes, we can. We can actually solve, in the next example, we're not going to do it, but we're going to basically notice that we can cancel out one of the radiuses, and we end up with K Q over R equals the mass of the electron times the velocity squared.